Chris, do you have quarantine requirement in Singapore?
No, not anymore, actually.
Oh, okay, okay.
We just recently lifted it, and now we can enter without quarantine.
Okay, okay. I should visit you and Marco at some point.
Oh yeah, I should definitely do that. Yeah, it's quite close.
I also want to go to ICT this year.
Yeah, I'm also planning to go. I haven't really laid it out yet, but we have submitted some papers.
Yeah, but we still have quarantine requirement in Taiwan, so that would be a bit annoying.
Is it okay? Also, what is it? QCredit is going to be in Taiwan, isn't it?
Yes, but it will be only virtual.
Oh, is it?
Yeah.
Oh no, I was looking forward to coming in person.
Yeah, because if you come, you have to be in quarantine for 10 days, and
that's longer than the actual conference.
Yeah. Okay, I think it's about time. So we are very happy to have Dr. Christoph Hirche to give us a talk of his recent work. And Chris is now a joint postdoc with Technical University of Munich and CQT of National University of Singapore. Chris is an expert in quantum information theory, and he has done many great jobs on quantum entropy inequalities, quantum hypothesis testing, and quantum communication. So today he will talk about capacity bounds via partial orders and complementary. So let's welcome Chris.
Thank you. Okay, thanks for the nice introduction, and thanks for having me at your seminar. Yeah, the topic of today's talk is going to be capacity bounds, and okay, that's a fairly long title, but we'll go through all the details in the next few slides. And this is joint work with Felix Weditsky, and you can find the archive number on the bottom of the slide if you want to check out more details later. So let me go through what these different terms in the title all encompass, and let's start with capacity bounds. So if you want to talk about capacity bounds, I first want to motivate a bit more broadly why we look at this in the first place and what the underlying questions are here. And I want to say, please, at any point of the talk, feel free to interrupt me if you have any questions or if I should go slower or faster on anything. So the general problem we look at here is that of information transmission. And of course, that's something all of you are very familiar with in your daily lives. So every time you connect your computer or your smartphone to Wi-Fi or to the internet, you use some form of coded information transmission and via some noisy channel. So your let's say your Wi-Fi, of course, everyone knows Wi-Fi is not always super reliable, and there's some kind of noise that prevents us from transmitting information more efficiently. And depending on what mode of communication you use, the noise model that you have to consider in order to transmit your information reliably is different. And a very natural question here is, what is the maximum amount of information that you can transmit via such a noisy channel? And classically, that's actually a fairly old question. It was first considered by Claude Shannon, and he defined the capacity of a classical channel. So that is the optimal rate at which you can transmit information per channel use in really like the limit of many channel uses and so on. So really the optimal rate. And more recently, of course, as you all know, people have kind of started developing these quantum computers, and we are looking more and more at quantum information. So at this point, it's not really sufficient anymore to transmit classical information over a classical channel, but we have to consider a new model, which is a quantum channel. And the capacity bounds I want to talk about are really in the same spirit. They encompass what is the optimal rate at which we can transfer information over a quantum channel. And throughout the talk, I will use these curly capital N's to denote quantum channels, and mathematically those are CPTP maps, so completely positive trace-preserving maps if you look at it mathematically. And yeah, we will see that the capacity of a quantum channel is generally much more complicated than that of a classical channel for several reasons. And the first one is already that there's not just one capacity. So it's not just quantum information over a quantum channel, but there are many more options. And I first want to introduce in a bit more formal way the two main capacities we're going to look at. And these are the quantum capacity and the private capacity. And so I know I'm trying to have the talk in a way that if you are already kind of familiar with all these quantities and so on, that you hopefully get like some of the technical details. But even if you're not too familiar with it, I just want to give you like the overview and the most important like takeaway points. So these are two typical tasks. And the first one, the quantum capacity, is kind of the most natural one, where we want to transmit quantum information over quantum channels. And I borrowed these pictures from the book of Mark Wilder. And the idea here is that we have some party, Alice, and she prepares a quantum state, which just naturally has some purification onto a larger reference space. And she encodes the state and then sends it over n copies of our quantum channel. And we have a second party, Bob, who tries to decode this, this information and to recover at the other end the same quantum state as well as possible. And importantly, he also recovers the correlation with the reference system. And the quantum capacity now, which I denote as Q, is the optimal rate at which we can send quantum information if I consider the limit of n to infinity, like n many channels and n going to infinity, and arbitrary encodings and decodings on Alice and Bob's side. Okay, so this is kind of the most basic capacity. And then we have one more example that I'm going to talk about in a bit more detail, which is the private capacity. So now we actually have a mix of like classical and quantum setting, in the sense that we want to transmit classical information over a quantum channel. But in addition, we also have the requirement that this information should be kept private. And there's one kind of important small mathematical concept implied in this. That is, if I look at a quantum channel n, I can always think of this quantum channel as an isometry on a larger space. Okay, we'll see a mathematical write-down of this in a bit on the next slide, I think. But these isometries imply that, so they are on a larger space. So we still, if we trace out what is new, we get back the channel to Bob, the channel n. But there's also more, which just goes to the environment. And often we think of the environment here as some eavesdropper. So we like to call him Eve. And the goal of the private capacity is to transmit as much information as possible, classical information from Alice to Bob via a quantum channel. But by considering the isometry of the channel, there's also some leakage of information going to the eavesdropper Eve, and we want to keep this classical information private from Eve. And then P is a private capacity, and it denotes again the optimal rate at which we can do this in the limit of infinitely many channels. And just as a remark for now, just from operational interpretations, you can, or operational considerations, you can often make statements about the relations of these capacities. And one can quite easily see that the private capacity is always larger than the quantum capacity. Okay. So this is just kind of the starting point. And now we have to unfortunately look into some more details on these capacities and look at the mathematical formulations. So in the classical case, so the entire classical case, Claude Shannon actually gave us a mathematical formula that allows us to really calculate this capacity of a classical channel. And nowadays, even in the quantum setting, we do have formulas for these capacities. Also, they're unfortunately a bit more complicated than what we get in the classical setting. And again, here, I'll have all these formulas on the slide. But if you're familiar with it, that's great if you understand all the entropic quantities and so on I write down here. But if you're not too familiar with them, then I want to kind of give you like two main takeaway messages from this slide. And the first one is we do have, well, okay. First, we do have an expression for the quantum capacity. But as you can see here, the quantum capacity is actually a formula of some simpler quantity Q1 that we call the coherent information of the quantum channel, but which then has to be evaluated on n copies of the channel. And we have to take a limit of n to infinity. So this is something we generally call regularization. And it's something that really makes it hard to calculate this quantity. So like, in fact, in most cases, we don't actually know how to calculate this quantity. There are only certain special cases, which I will talk a bit about later, where we know how to calculate this quantity, but generally it's very hard to do that, or we don't know how to do that. And this is in contrast to, for example, the classical capacity. For the classical capacity of a classical channel, we do not require such regularization. In that sense, we say the classical capacity is additive, while the quantum capacity is not. It's actually super additive. And we really need to consider this regularization for general channels. And then this Q1, for the details, might not play like a big role what these entropic quantities are, but the Q1 is a fairly simple quantity, at least compared to the actual capacity. The limit here is really what makes most of the problems. And besides the regularization, the second point I wanted to point out is that this Q1 formula, it can be written as a difference of two entropic quantities, which are mutual information. So again, if you're interested in the details, the definitions are here on the bottom. And the main thing I want to point out here is that this is a optimization problem over so-called CQ states. So these states have one classical and a quantum part. And the quantum part here is restricted to pure states. But what I mostly want to point out is that these two terms, they each depend on a particular channel. So the channel from A to B is our original channel. So the first term depends on this original channel. But the second term we calculate on what we call the complementary channel. And since this was one of the words I used in the complementarity in the title, I should like properly say what the complementary channel is, and this will be important throughout the talk. And this is kind of what I mentioned on the previous slide. So every channel N, I can enlarge it into an isometry, and here on the top right, I call this isometry V. And now I can rewrite my channel as an isometry that goes from A onto the larger space B plus an environment E. And if I trace out the environment, I get back my original channel. Okay. And this channel, of course, A to B, it models information flowing from Alice to Bob. But now we have this environment, and we can also be interested in the information going from Alice to this eavesdropper. So if instead of tracing out E, I trace out the system B, I get a channel, a new channel that's like a valid CPTP map as well, that goes from Alice to the environment. And this channel we call the complementary channel. And that's not just an arbitrary choice. These channels are kind of unique up to like a choice of unitaries or isometries on the environment system. Okay, so that's kind of all the starting point we need. And really one of the things that are really the takeaways is what is a complementary channel, and that the quantum capacity is this complicated formula that's a regularized version of some simpler entropic quantity. And for the private capacity, we have a very similar picture. And again, the main takeaway here are that the private capacity can be written, or has to be written, as a regularization of a simpler entropic quantity. And the simpler entropic quantity looks very similar to the formula we had on the last slide, the difference of two mutual informations, just that we now have to optimize over a larger set of quantum states. And the main difference here is that the quantum part of these states, we have to optimize over all mixed states instead of pure states. And as I mentioned before, we can easily have like relations between these different capacities. Sorry. And we see, for example, that the quantum capacity is always smaller than the private capacity, and the same for the kind of one-shot version or the single channel version. And now we can also see this mathematically simply by noting that there's an optimization over a larger set of states in the private capacity. Okay, so much about kind of like the technical introduction of these capacities. And now I want to do just some warm up and to kind of like the theme of the talk, and also tell you about a few more capacities, also not in the same detail as before. And so we already had quantum communication over a quantum channel and private classical information over a quantum channel. But we can even be less restrictive and just consider classical information over a quantum channel, so now without a privacy constraint. And the optimal rate at which we can do this task asymptotically is the classical capacity, usually denoted by C. And the classical capacity itself is again a regularized formula. And the simpler, like one channel version of this quantity is the Holevo quantity right up here. So for this case, the exact like entropic definitions don't really matter so much. And the third capacity we can look at is the entanglement assisted classical capacity. So this is again classical information over a quantum channel, but we allow for like an aid of entanglement on the side that helps us to transmit more classical information. And as with the previous capacities, we can actually relate these quantities quite easily to capacities we have already seen. For example, the classical capacity is always larger than the quantum capacity. And that is quite intuitive, right? The transmitting classical information is generally easier than transmitting full quantum information. And kind of the first warm-up I want to talk about to the theme of this talk is the first small result. That is, if you play around with the entropic definitions of these quantities for a while, you actually see, and it's not too complicated, especially for the first two, that we can also upper bound these classical capacities. And these bounds you get are kind of, they mirror in the first part always the lower bound, and they get an extra kind of penalty term that is based now solely on the properties of the complementary channel. And these bounds are kind of to exemplify that the complementary channel actually plays, or the power or the capabilities of the complementary channel, they play a crucial role in kind of determining how powerful, in some sense, the actual quantum channel that we are looking at is. So I think I want to briefly talk, for example, about the second line. And we can see here like some easy, like intuitive interpretations of these inequalities. Like one is, for example, if we are not able to send any classical information to the eavesdropper via the complementary channel, so this classical capacity here in the very end is 0, then we see that this usually not very tight inequality actually becomes an equality. So the classical capacity then is equal to the quantum capacity. And similarly, we can see that if the quantum capacity of a channel is 0, that means that it's always easier to send classical information to the environment than it is to send it to our actual receiver. And similar interpretations hold, of course, for the other inequalities. And this kind of like a motivation, or this is our first small results, but it also serves as a motivation to see how much of this interpretation that the complementary channel bounds the power of a quantum channel also holds for this more interesting, like quantum and private capacity. And for that, we have to talk about the last part of the title of this talk, which was partial orders. And partial orders are like a commonly used tool to kind of make the calculation of capacities easier. And the first one I want to talk about, simply because it's the most general partial order. Oh, sorry, not most general, the most commonly used partial order is degradability. So we can just stick with this second definition here. We call it channel M, a degraded version of a channel N, if there exists another quantum channel. So we can simulate M from N by just adding D to the mix. And so this is a degraded channel. And then a particular channel N, we call it degradable if the complementary, no, if it is a degraded version of the complementary channel. Sorry, the other way around. If the complementary channel is a degraded version of the channel. And then we call it anti-degradable if the opposite holds. Okay, and these are really two commonly considered classes of channels. And the main reason for that is that they give very nice properties to capacities. So what is known is that both for the degradable and the anti-degradable capacities, all these capacity formulas I talked about in the beginning, so the private capacity, the quantum capacity, and the corresponding single channel versions, they all become equal. And in the case of the anti-degradable channels, what is more, they're not just equal, they're actually all equal to 0. So these are two classes of channels for which calculating capacities becomes much easier. And this is kind of an idea. Well, this is well known, but it's something that we want to build upon in the rest of the talk. And for the actual content of the talk, we have to introduce a couple more partial orders. And I start with partial orders commonly known as less noisy. And less noisy was originally introduced in classical information theory. And there it was introduced as an inequality between two mutual informations. And you might recall that these are the same two mutual informations that appear in the definition of the private capacity. And it was actually Watanabe in the paper that I mentioned on here who realized that these can be again connected to the private capacity or give a condition on the private capacity. So we call a channel less noisy if the private information, so the non-regularized private capacity, is of the complementary channel is 0. So well, it's easy to see that this is a partial order on the set of channels. And this is kind of the most direct generalization of this classical concept of less noisy. But because things are always a bit more complicated when we look at quantum information, there are actually many ways of generalizing the less noisy partial order to the quantum setting. And interestingly, all of these are going to be useful going forward. And of course, one other natural generalization is to regularize this condition. And this is equivalent to the private capacity of the complementary channel being 0. And we can also, instead of optimizing over CQ states, we're here or like checking this inequality for all CQ states, we can actually check it for all quantum states, like fully quantum states. And this is what we call the fully quantum less noisy order. And we can associate it with a like capacity-like formula, which is again very similar to the private or to the private information, just that we optimize over all mixed states. And this quantity, I should say, or not this quantity, but this partial order has been previously considered by Crossley and Smith. And in their work, they called it information degradability. And also this quantity here, the PE, also I haven't introduced it yet, or I haven't introduced it in detail. It does actually bear at least some operational interpretation in the sense that it was shown to be the entanglement-assisted private capacity of a degradable channel. And there's still some questions around this quantity, for example, what operational interpretation has for non-degradable channels. But so there's at least some operational meaning to this quantity. Also, I don't want to go into full details in this talk. And the other set of, okay, so this is one set of partial orders. The other set of partial orders I want to introduce is the more capable partial order. Again, this is a generalization of a classical concept. And as you noticed, not much on the slide has actually changed when I moved. So now we replace in the names of the partial orders every less noisy by a more capable. And in exchange, all the private information and private capacities here, the P's, are replaced by Q's. So for example, now a channel, we call it N regularized more capable if the quantum capacity of the complementary channel is 0. Okay. And again, for the entropic inequalities, every mixed state is simply replaced by a pure state. So this mirrors again the relationship between the private and the quantum capacity. Okay. And now we'll have to look at some literature results. And this was also, the first one was also realized by Watanabe. And he noticed that some of these equalities that I earlier showed for degradable or anti-degradable channels, they don't just hold in this kind of restricted setting, but they hold more generally for this more capable and less noisy orders. Oh yeah, I should probably have said that it's quite easy to see. So that degradable is kind of the most restrictive of these conditions. And the set of degradable channels is included in all of the other partial order, like sets defined by all the other partial orders. And more capable is an even weaker, or it's a provably weaker requirement than less noisy. So really the weakest one we consider is this more capable condition. And Watanabe showed that if a channel N is more capable, then the single letter capacity, so the private information and the coherent information of a channel, they're actually equal. And if we allow in our condition for the regularization, then the actual capacities are equal. And what's more, if we, instead of more capable, we consider less noisy, then all four of these quantities again are equal. So this mirrors what we earlier saw for degradable channels. And yeah, so this kind of just gives us larger sets of channels for which the same like easy formulas for these hold. And remember again that the definition, by definition, these partial orders more capable and less noisy, they can be defined solely as a capacity restriction of the complementary channel and not of the channel itself. Okay, and a second result from the literature I want to briefly discuss is by David Suter et al. I have the archive link here if you're interested. And those guys defined, or they took the class of degradable channels and they kind of relaxed the condition. So instead of requiring the condition for degradable channels exactly, they just required to hold approximately in diamond norm, so up to some error epsilon. And the resulting class of channels they call epsilon degradable. And now we saw that degradable channels have all these nice properties. And they can show that, or they showed that these nice properties still hold approximately as long as degradability holds approximately in the sense. Yeah. And of course, now we have these two results. It just seems natural to think, okay, what happens if I think of more capable or less noisy partial orders also in an approximate sense? Okay, and this has actually been very recently done by Cambridge Rouge, Daniel Steele-France, and myself in the paper that I mentioned here on the bottom. So we defined a relaxed version of these partial orders. And again, the details are maybe not that important, but they're kind of, it's like a straightforward generalization of the partial orders by just allowing for an epsilon error in these definitions. And in particular, for example, if I look at the less noisy partial order, that you remember it required the private information of the complementary channel to be 0. We now just require it to be smaller than some constant epsilon. Okay, and one of the results in this paper was that we can again take these simpler versions or these nice equalities for the capacities, and they still hold approximately if the partial order holds approximately, or if these conditions hold approximately. So for example, if a channel is epsilon close to being regularized more capable, then the quantum and the private capacity cannot be different by more than an epsilon. And now based on this, now you can ask, of course, can we make a more general statement? A statement that actually holds for all quantum channels, and that is more in the spirit of the inequalities for classical information that I showed you earlier. And this is kind of one of the main observations of this talk, that indeed we can. And the observation is mathematically, it's not actually very complicated. Just by the definition of how we set up these classes of approximate more capable channels, we can ask under which conditions is actually every channel, let's say epsilon regularized more capable. And of course, every channel is if we just choose epsilon large enough. And we can choose epsilon to be the capacity of the complementary channel, and then we see trivially that this holds for every channel, right? And this gives us a set of new inequalities that are bounds, that are upper bounds on quantum capacities. And I have listed kind of the main results of this section here in this box. And let's just take one of them as an example. Let's say the first one. And we have already seen in on the previous slides that the quantum capacity is always smaller than the private capacity. And the same for all the ones below. The first inequality is kind of something that's well known, that follows just from the definition or from the operational interpretation. But what is new now is that we can also upper bound these quantities by the by a capacity which matches the lower bound, so in this case the quantum capacity, plus a penalty term that depends or seems to depend solely on the complementary channel. So we have, in this case, for example, the private capacity is upper bounded by the quantum capacity of the channel plus the quantum capacity of the complementary channel. And of course, all the previous results, we can get them back from this as special cases. Of course, if this is bounded by epsilon, then we get the results from the last slide. And if a channel is actually regularized more capable, so this here is 0, then we see that the quantum and private capacity are actually equal. And we can also, using some simple continuity arguments, get back the results on approximate degradable channels, which means actually that these inequalities are at least as tight as also an epsilon approximate, an epsilon degradable channels. And but the main motivation here is really that beyond giving us like upper bounds, these upper bounds, in contrast to what has mostly been seen in the literature, have a very clear and nice operational interpretation. And like I said, they're also tighter than many of the bounds that we know. But there's, of course, one big downside is that now I'm writing these upper bounds in terms of capacities. And we have seen on one of the very first slides that these capacities are regularized formulas that are very hard to compute. So it's not necessarily a bound that always allows us to really give like a numerical bound, but that gives us a bound with a very nice operational interpretation that hopefully helps a bit to like better understand the interplay between different capacities. And okay, I have a note on the bottom of the slide, which is maybe only relevant for the experts, but if you want a bound that has a more operationally solid interpretation, then we also show in the paper that this PE quantity can be upper bounded by yet another capacity, which is a symmetric side channel assisted quantum capacity. But I don't want to go into too much detail here. Okay, so let me briefly talk a little bit more about these bounds. And okay, of course, like I mentioned, they have these nice operational interpretations, but we can also get some more things out of them. For example, some new insights that might help us narrow down new classes of channels. And the first one is that we can see from the first equality quite easily, of course, that if the quantum capacity and the quantum capacity of the complementary channel are both 0, then the private capacity has to be 0, which was, as far as I know, not known in this form. And this actually will become relevant again later when I talk about some open problems or some directions for further research. In the sense that we don't know actually many classes where the private capacity is 0. And those classes are actually very relevant, as I'll discuss later. And we hope that these kind of these inequalities might help in some way to find new classes of 0 private capacity channels. And the other thing is, the second point I want to mention is that while these quantities themselves, not all of them are like easy to compute, especially like the capacity, of course, is not easy to compute. It still allows us to sometimes get new numerical bounds. And we have an example of that in our archive manuscript, if you want to check it out. But the essential idea is that there actually there's a lot of research on upper bounds on the quantum capacity, like good numerical upper bounds. But there's somewhat less research or less results on this on the private capacity. And our upper bounds allow us to directly kind of apply upper bounds on the quantum capacity to the private capacity and get like some decent numerical results there, at least in certain cases. Okay. And I don't know, really feel now I'm kind of, this was kind of the first part. So also feel free to interrupt me with any questions if you have any. Otherwise, I want to briefly move to kind of like an interlude. I want to move from quantum channels just for, I think, 2 slides to quantum states. And the same way we think of a quantum channel usually as some kind of dynamic resource, we can also think of a quantum state as a static resource. And in this case, we can often distill certain resources from a quantum state. And the ones I'm mostly interested in here is distillable secret key and entanglement. So we can distill these resources from a state. This comes from very similar, or these are very analog definitions to the capacities earlier. We can define the optimal rate at which we, with certain limited sets of operations, we can distill secret key or entanglement from quantum states, right? And these are really like interpretation-wise, these are very similar to capacities, or they are basically capacities on states instead of channels. And these are the 2 I want to focus on here. And the question is, of course, can we define partial orders on quantum states in the same way as we do on quantum channels? And indeed, of course, we can. We just have to take an operational quantity as we did with the quantum or private capacity and replace this with an operational quantity on states. And in particular, I picked these 2, the distillable key and distillable entanglement, and especially in the setting of one-way assisted distillation, we know actually precise formulas again for these state capacities. And using these, we can also somewhat define partial orders on quantum states, of course. And for that, we define the concept of a complementary state. Okay, and if I start with a quantum state rho AB, so a bipartite state on 2 systems, then I can always purify the state to involve a larger state, a pure state that also has a system E. And if I would trace out E, of course, I get back AB. But alternatively, I can trace out the system B, and the state I get is what I call the complementary state of rho AB. Okay, so this interpretation is very similar to what we did with the isometries in the quantum channel case. And now I can define partial orders on the set of quantum states in the similar way to channels. I call, let's say, it's channel more secret, or in this case, particularly regularized more secret, if the one-way distillable key of the complementary state is smaller than epsilon. So this is already by default the epsilon approximate version of the statement. And similarly for distillable entanglement, and then we call this partial order more informative partial order. Okay. And I don't want to go to too many details, also in the interest of time. But I just wanted to briefly mention here that using these partial orders, we can actually get very similar results on quantum states. So we get a whole bunch of inequalities that mirror what you saw on the quantum channel case. And in particular, let's just, for example, pick one of these to look at them briefly. So for example, the first one, we see that the distillable entanglement, okay, we always know that, again, mirrors the channel case, that the regularized versions are larger than the underlying like one copy quantities. But we can see that these are also upper bounded by the very same quantity plus a penalty term that solely depends on the complementary state. Okay, so these operational interpretations that we got for quantum channels, they kind of translate to these static resources of quantum state and distilling secret key and entanglement. And we get, similarly to the previous case, we get lots of results back in some way. If, of course, these terms are zero, then all of these inequalities hold with equality. And we also get like operational bounds in some way. Like the power of the complementary state bounds how well we can do with the state itself. Okay, so this was just meant to be a brief interlude about static resources. And if you have more questions about this, please feel free to ask me any questions, or also have a look at the preprint. And now for the end of this talk, I want to come back to the channel case and discuss a bit about some open problems that kind of arise from here. And the first kind of important open problem is that I introduced all these like new partial orders, or well, not new, but like these different partial orders that then, for example, we saw that the regularized less noisy order recovers many of the things that we previously only knew for degradable channels. But now an important question is, are these two sets of channels actually different? So in many cases, for example, if we compare more capable to less noisy, then we know that these two sets are different. And that follows simply by there are channels that have a larger private capacity than quantum capacity. But in this particular instance, regularized less noisy and degradable, we do actually not know of any channels that lie in between these two sets, like that are less noisy but not degradable. And this, I think, is one very important question that also is interesting beyond like the topic or the direct topic of this talk. And one kind of corollary that follows from the considerations that we make in our work is that this question is very closely connected to another important open problem regarding the private capacity, which is that of superactivation. And I should briefly explain what superactivation is. So we saw earlier that that private capacity and quantum capacity are super additive. So considering more than one copy of a channel can give you an advantage when calculating these quantities. That's why we need the regularization. And superactivation is an even stronger form of that. If I have two quantum channels for which the private capacity is zero, but the joint capacity, if I use both of these channels together, is strictly larger than zero, then this is what we call superactivation. And interestingly, we do not know of any examples where the private capacity can be superactivated. But in contrast, if we look at the quantum capacity, then we know precise examples where superactivation is possible. So for the quantum capacity, we know that it can be superactivated. We do not know that for the private capacity. It's an open problem. But one corollary that I want to come back to now is from our work is that if P can be superactivated, then the class of degradable channels has to be a strict subset of the class of regularized less noisy channels. Okay, and yeah, so this kind of like more tightly connects these two concepts and these two important open problems. And we hope that our bounds can somehow play a part in like resolving these two questions. And how exactly we thought about this, I want to discuss on what I think is my last slide. So can P be superactivated? And I want to go back, like I mentioned, the quantum capacity actually can be superactivated. So there are two channels which both have zero quantum capacity, but the joint quantum capacity of the two channels is strictly larger than 0. And the important observation here is that we need two separate classes of channels with 0 quantum capacity. And the only classes actually that we know are the ones with antidegradable channels. So this one I introduced earlier, and we already saw that this always has 0 quantum capacity. And the other one is the class of PPT channels. So this is the class of channels where whatever state we input, the output state is always PPT, which means positive partial transpose. And this is the second class of channels that we know of with 0 quantum capacity. And in fact, if we suitably choose two channels, one from each class, then the quantum capacity can be strictly larger than 0. And this observation that we need channels from two separate classes is actually important, because it's also quite easy to see if I, for example, take two antidegradable channels, and their combination will always be antidegradable as well. So taking two channels from the same class generally doesn't lead to a positive capacity. And this motivates also for the, well, similar holds for the private capacity. And this motivates the search for new classes with 0 private capacity, new classes of channels with 0 private capacity that way. And okay, one idea that we bring up in our paper is, of course, to use our bounds to find these classes. And what we saw is that the private capacity is upper bounded by the quantum capacity plus the quantum capacity of the complementary channel. So if one can find a channel that we call bi-PPT, that means that a channel is PPT, but also its complement is PPT, then our bounds show directly that that the private capacity also has to be 0. And our hope was that if one finds such a channel, this would be a good candidate to show superactivation of the private capacity. And in turn, this would also be a good candidate to show that degradable channels and regular as well as noisy channels are not actually the same set. And of course, the resulting question here is, does there exist a channel that is bi-PPT but not anti-degradable? Okay. And okay, now I can make a brief remark, which is that I planned out these slides very nicely, but then just this morning I learned that there's going to be a paper forthcoming by some colleagues that actually shows that the answer to this last question is no. So unfortunately, there does not exist a bi-PPT channel that is not anti-degradable. And if you're interested in the details, you should have a look at the archive in the next few days for a paper by Müller-Hermes and Singh. And there you'll find all the details on resolving this open question at the very end. But okay, that means that kind of this particular approach does not work to find superactivation of the private capacity, but the overall scheme still remains. So if one can find a new class of 0 capacity, 0 quantum capacity channels, then one can always define these bi-classes or some mixed version of, let's say, PPT and this new class or something that would imply immediately 0 private capacity. And then any of these channels, if they're not anti-degradable or if they're not in any of the known classes, they would provide promising examples of where to search for superactivation of the private capacity. And of course, it remains an interesting open problem if any of these channels actually exist. Okay, and I think that is all I wanted to discuss. And I thank you all for your attention. And please feel free to ask me any questions if you have any.
Thank you, Chris. Can you go back to the open problem slide?
Sorry, to which slide?
Open problem slide.
Just this one?
The previous one.
Yeah.
Yes. So does this question be answered? Does there exist a channel that is regularized, less noisy, but not degradable?
No, I still don't know any answer to this question.
Okay, so there, the new forthcoming paper didn't address this question, I guess.
No.
Okay.
The paper I mentioned, it will show that every bi-PPT channel is automatically also antidegradable. So it excludes one class of channels to search, but there's still, I don't know, there might be hope that either the superactivation or the separation of these classes might still be possible. Just you have to find a new class of channels.
Okay, so this question has been answered. It's different from the one in the previous page.
Yes.
Okay.
Yeah, this is like, okay, this is kind of the big open problem. And then this one is just like, this was our approach to this question, but apparently this approach is not possible.
I see. Okay. Okay, I have yes. Wojin, you can go ahead.
Just is there any question from the audience in this room? Okay, we have a question here.
Hello. Thank you for your talk. Yeah. Sorry, I am not the expert, but I'm just asking if I understand correctly. You are using the partial order in the approximate form, and you are trying to use the private channel to improve the bound, or what's the role of the private channel? Why can it help?
Oh, okay. So briefly go back to the, yeah, maybe this, no, sorry. Oh, I went back too fast. Okay, maybe here. Yeah, so okay, that's a good question. I didn't go too much into the proof details of how you actually show these inequalities, but the proofs are essentially like entropic proofs. But it turns out that the optimal values for these epsilons, so we use these approximate partial orders like in the entropic version to prove these inequalities. And it turns out that the optimal epsilons, they correspond to these capacity formulas. So in some way, we restrict this class of approximately more capable or approximately less noisy channels in size by fixing this capacity bound. So the capacity of the complementary channel tells you how close we can make kind of the ring on this class of channels, or how small we can choose this epsilon. And that's kind of the crucial point. And then we get these inequalities kind of from these entropic considerations. I don't know. I hope this answers the question.
So does this all routine in the super additivity that if you have more channel resource, then you can improve the bound? It is the very root. I'm not sure if I asked correctly.
So you're asking about the super activation of the channel. So for example, the third inequality here, the super additivity. Am I getting that correctly? Yeah, exactly. So also for the super additivity, so comparing these regularized quantities to the like the single copy quantities, one knows easily like super additivity tells you that the regularized version always has to be larger than the single shot version or the single channel version, which is very easy to see. But these bounds kind of tell you that the information transmission capabilities of the complementary channel, they bound how much advantage you can get by regularizing. So if these kind of, in this case, what corresponds to the entanglement assisted private capacity, if that of the complementary channel is 0, then regularizing does not give any advantage. So there's no super additivity. The quantity actually becomes additive.
I see. Okay. Okay. Thank you very much.
Thanks for the question.
Chris, I have a question.
Mm-hmm.
So now we can use the complementary channel to bound some other entropic quantities. So now I'm wondering, does it hold for the case of Renyi version of mutual information instead of the standard mutual information? And it reminds me of some duality or uncertainty bounds proved by Markov or in his book, at least in the state case, because they also consider the three partite states, and then I remember that they derive some uncertainty of duality bounds for the Renyi conditional entropies. So that's why I'm wondering the relation, because here it looks very similar to that, because it is complementary state, at least for the state case, is very similar to their study. So that's why I feel like maybe there's some relationship, like those qualities in terms of the Renyi version of the entropic quantities instead of the alpha 1 version.
Yeah, that's a very interesting question. Okay, to be fair, I haven't thought about this too much. But so one thing that would be, of course, an interesting, okay, first part of the question, Renyi entropies. I think this is like an interesting question, in particular if you look at like smooth Renyi entropies or something. And I wouldn't be surprised if something similar holds for like the corresponding, for example, one-shot capacities. So really the ones that you define in terms of like smooth min and max entropies and so on. But of course, with these smooth quantities, you don't have like exact, with the one-shot capacities, you don't have like exact expressions for the capacity. You rather have lower and upper bounds and so on, and then one has to be a bit careful. But yeah, I think in a similar way, maybe one could look at these things like Renyi versions of these statements by looking at one-shot capacities and so on. I think that would certainly be interesting. The second part of the question, the uncertainty bounds. I mean, I think there's really like a spiritual connection. But in terms of proofs, I would say they're actually quite different, these complementarity bounds and the uncertainty relations. Like these are really the main tool for proving these entropic things is, I mean, these capacity things, it's really like chain rules and stuff. So they're really just like basic entropy properties kind of that we use.
Yeah, and I guess there are also some chain rule properties for the Renyi version of Renyi type entropies, either for the smooth one or not smooth one. So I think that would be interesting to extend your ideas to the one-shot case, at least for those Renyi type entropies.
Yeah, definitely. Might be definitely an interesting problem to look at.
Okay, I think it's about time. So let us thank Chris again for this very fantastic talk. Thank you.
Okay, thanks for having me.
Okay, so I guess I'll see you at some point.
Yeah, hopefully soon. You're welcome. You're welcome to visit here anytime. I just hope the quarantine requirements are going to be lifted soon.
Yeah. Okay, thank you.
Okay, thank
Bye.
you. Bye.